Hello, hello. Well, I'm back. I can't sleep. And why I can sleep? Well, our beloved friend Ian Lecan raises $1 billion in Europe, in Paris, for his startup AMI. And he's still wearing meta glasses for some reason. He said he doesn't like them, so maybe it's an old picture. But yeah, why people are so excited about this? And the answer is brainchild from Meta, called JEPA. So JEPA stands for Joint Embedding Predictive Architecture, and this is the reason why I'm doing this tutorial, to kind of explain the basics and historically where it came from. And like, yeah, this looks like a nice diagram. There is a lot of interesting things happening here. But the main concept is you have, when you talk about joint, like a joint distribution or the joint in my bathroom, is that you need to have some sort of two variables. So two variables can be present, future. It can be maybe multimodal. So it can be, I don't know, stock price and the weather, or something like that. And well, the difference, as you can see here, you have two encoders, right? Then you have an action. So this is what the agent does to the environment. And this action, well, should affect your outcomes. Otherwise, you are in not a controllable state. But yes, you need to have this magical Z. So Z is this latent variable. And you have a predictor that takes the encoded state, and Z, with some sort of conditioning, A gives you the next state. So you are doing a glorified next state prediction. But very importantly, you're doing that in latent space, which is the kind of innovation here, if you would ask me. And yeah, well, I mean, this is one part. The other one is that how do you do this? And you have this concept of energy-based models. In fact, if we see what he released recently, he released the Kona EBM, and notice that. So that's, well, this is what it's an energy function, guys and gals. And well, you have a ball. Maybe this is gravity. And Kona is yeah, it's an energy-based model and the foundation of everything we build. Okay, blah blah blah. And you can use this to solve Sudokus. I actually solved Sudokus with a transformer, which I will show you maybe in another tutorial. But yeah, you can, let's see if it works today. You can actually solve a Sudoku, which is a CSP, via an energy-based model, which is super cool. And guess what? Most LLMs are unable to do that unless they memorize the solution. And there are also like very cool benchmarks about that. So if you have time, play with this. It's really fun to watch how they didn't solve that. And so yeah, okay, so yeah, it's an energy-based model, certainty, not probability. Interesting. And well, what is an energy function then? So I'm going to split this tutorial in two parts. And it sort of runs on Colab. And yeah, I don't want to keep it too long, so I'm going to just do the first part on energy functions. So let's start. So what is an energy function? So an energy function is a scalar value function that always gives a single real number an energy to every configuration you care about. So X is your portfolio or your happiness at work, something like that. Sorry, X can be like your number of hours, and the energy function can be the happiness or the salary, right? And so what you want to have is you want to be in a favorable state. So a low state means something that you is preferable, stable, likely. High energy means something you don't want to be, like, because it's unstable, incompatible, or unlikely. Well, it doesn't tend to be convex like in support vector machines, where you can find the optimal because you know it's a convex, or in a convex optimization problems, or smooth, or normalized, or even bounded. So it can be anything, like really crazy stuff. But it needs to have some key properties, which you can see. So it needs to be scalar, scalar output. It's all about, it's relative, not absolute. So like you only care about the difference. It's not a probability directly, but it can be transformed into one. And you can calculate a gradient on the energy. Some people confuse it, but effectively the gradient is the force in physics. So the negative gradient is the direction that lowers the energy, and vice versa. There could be multiple minima. Yeah, like you have to live with that. So energy functions. Think of it as a flexible scoring function. I made this very simple, silly chart here. And this is like, it's just like two Gaussians centered equally between 2 and -2. But yeah, it's just like an energy function. So it goes from 0 in this case to 0.96. So the higher is the darker is the lower one. And so you have two identical minima, because you can have many. And you can interpret these points. So this is a two-dimensional landscape. It can be like, I don't know, a map, or it can be like the sea, and like one of them there are treasures. I don't know, something like that, right? So it can be anything. So it can be like your state space, and then the energy gives you some sort of preference, like this is where you should be, right? I don't want to be here because maybe it's really risky. I want to be in these two states ideally. And so like if you're here, it's high, it's unstable. If you're here, it's the minimum. And in physics, well, you are sort of bounded by the law of physics. So you can well, I guess you can fight gravity, if you build a plane. But the idea is that you if you look at classical mechanics, you have the concept of potential energy, which is depends. So if there's gravity, it depends on the height, and there's a formula. So essentially, the higher you have, the higher potential energy you have, and then it sort of transforms to kinetic energy, because when physics, energy doesn't disappear or creates. But okay, essentially, so once you have this potential energy, which is the V, you can calculate the force, right? Which is the kind of negative gradient. So when you see this symbol here, is actually the gradient of the actual potential, which is an energy. Then, well, what happened in statistical physics? Boltzmann came up with this beautiful idea that essentially sort of maps out the energies to probabilities. And if I remember correctly, it was through the Brownian motion. So what happens is that, and I think it's you have the temperature of this system, and so you have the thermal equilibrium is the probability of finding a system in a state X. Is proportional to the exponential of minus energy divided by K per T. And so basically, low energy means high probability, and vice versa, high energy means low probability. So, and this is exactly the same thing we use in EPMs. So the temperature T controls the kind of sharpness. So high temperature flattens the distribution, so everything becomes very equiprobable. But if you decrease T, the probabilities concentrate at the minimum. And so the T is that parameter that you usually play with in LLMs, because the LLM have a softmax to produce the next token. So if you change T to very low, you have very predictable, let's say, boring tokens. But if you increase T, you get some random rubbish most of the time, right? You just it's like drunk. And there are, of course, other examples which I found online and that don't really understand. I mean, I remember Lattice from crystals. But the reason why we have these kind of crystals that are very incredible regular structures is they always go into these lowest energy states. Protein folding, well, if you remember DeepMind, AlphaFold is basically an energy minimizer, right? And Hopfield, the spin glass, you have this the magnetic spin freeze into one of many low energy patterns. And so bubbles, yeah, I mean, you minimize the surface area versus the surface tension. I think my kids are studying that in school. So yeah, the main theme is we want to go if you have a system with an energy function, just give it enough time and it will find its own valley. Now, it doesn't mean it's the best minimum. It will go somewhere where there is a minimum. It doesn't mean it's the global minimum, but it will go naturally there. Unless you use an external force to fight gravity, like a plane. But yeah, that's also another interesting concept. And, well, the other things we have is that energy functions have been used in previous machine learning models, right? And they all had this problem, the Z, okay, the partition function, which is, you have to be careful, it's not the same Z, the latent, that we saw in the previous diagram. Unfortunately, they're called the same. But yes, in any case, in machine learning, we had something like, we have Hopfield networks, Boston machines, which you mentioned, RBM, CRFs. And the kind of punchline is all these require approximating or avoiding this Z, this partition function. And the modern EBM that we're going to show in this tutorial is like you somehow magically avoid it altogether during training by using a trick, okay? The way you sort of people have used to do that, did I write it there? Yes, is that you essentially, we all became from Boltzmann machine, and then we went to contrastive EBMs, and then JEPA, and this is what we want to do in this tutorial. So I'm going to stop now and wait for the next part.